Okay, so when we are talking about our alkanes, can somebody go ahead and just tell me what do you guys know generally about the structure of alkanes? What do you know about them as a homologous series? Zoya, do you want to go ahead and start? Just like let me know what you guys already know about. Yeah, yeah, go on.
Alkanes are like they're saturated.
Yeah, good. They are saturated. They're definitely saturated molecules. They're considered to be hydrocarbons. What are hydrocarbons?
They're molecules with only carbon and hydrogen.
Yeah, they're molecules with only carbon and hydrogen inside of them. And alkanes are saturated hydrocarbons. What is considered to be their general formula?
CnH2n plus 2.
Exactly. What is a homologous series?
A series of like molecules that have the same general formula and similar physical properties. Sorry, chemical properties.
Similar chemical properties, and the physical properties are going to be following a specific trend, right?
Yeah.
Okay, that's fine. That's correct. Now, when
They're
we talk
non-polar.
about the... Sorry?
They're non-polar.
Yeah, exactly. They are non-polar. Very good. And then when we are talking about our physical properties, so what do we know about the trend in physical properties of our alkanes? And why do we have this trend? You guys should know that as well, because we have done something related to it.
Their boiling point increases because when the number of carbon increases, they solidify.
Not exactly. Think about more in terms of, okay, Zoya especially should be able to answer this. It's fine if Aisha cannot because she wasn't there when we studied intermolecular forces and bonding. So we talked about this.
They have stronger van der Waals forces.
Yeah,
like
why do they have
forces?
Yeah, exactly. So when your number of carbon increases, the number of electron increases. So your van der Waals forces depend upon the number of electrons. Greater the number of electrons, the greater your number of van der Waals forces are going to be. So as your number of carbon atoms increase, the number of electrons increase, which increases the number of van der Waals forces. So you need more energy to break the bonds. That is why melting point and boiling point increases. And that is why the physical state also changes from gaseous state to liquid state. Okay, good. That is all fine and well. Then another thing we have to talk about is our sources of alkanes. What are the sources of alkanes? Where do we get alkanes from?
Is there crude oil?
Exactly, crude oil. Does anybody remember the principle of how we're separating the alkanes from crude oil? You don't have to know into details of it, but a little bit about it, you guys should have an idea. And you guys have done this. Yeah, fractional distillation. Not cracking, fractional distillation. I'm asking how you're going to separate your alkanes from crude oil. So that is done by fractional distillation, right? Fractional distillation allows you to separate them. Cracking is the process by which you take a large hydrocarbon and turn it into a smaller alkane and an alkene. Okay, that is cracking. The process that you use is known as fractional distillation, where you separate the crude oil into different alkanes or different hydrocarbons. Does anybody remember the principle of fractional distillation? Like even from your IG, because you guys did it in quite a lot of detail in IG. So does anybody remember what the principle was?
Like the order of what you get?
Not the order, like what the general principle is. How does it actually happen? What's the general concept?
You need a catalyst. You can use Al2O3 or SO2, and the temperature is going to be, I think, like 60 degrees.
The temperature is going to vary. Remember, you do the process in a fractionating tower. The entire process is done in a fractionating tower, and each level is going to have a different temperature. So there is no fixed temperature. Every level is going to have a different temperature, and you're going to do it in a fractionating tower. Okay. Do you guys remember fractional distillation? What was fractional distillation? Separation of miscible liquids from each other based on their boiling point. Okay, so what happens over here is that in your crude oil is a mixture of different hydrocarbons. Those different hydrocarbons are going to have different chain length, and because they will have different chain length, they will have different boiling points, right? So larger hydrocarbons are going to have a higher boiling point. Smaller hydrocarbons will have a smaller boiling point. So we separate them from each other based on their boiling point. That is the principle of fractional distillation, that we are separating the liquids from each other based on their boiling point. For example, those those hydrocarbons that have a boiling point around 260 degrees centigrade, those hydrocarbons will, when they reach the temperature of 260, they will condense, right? They will condense, they will turn back into liquid, because we know that boiling point is the same as condensation point. Boiling point is gas into liquid into gas, and at the same temperature, gas can turn back into liquid as well. So approximately when you reach the 260 degrees centigrade, then all those alkanes that have a boiling point close to this, they will turn back into liquid and they will condense over here. The rest of the alkanes that have got lower boiling points, they will stay in gas and they will keep on moving upwards. And when they will reach the area where the boiling point, where the temperature of the tower is going to match their boiling point, they will turn back into liquid, and the rest of the alkanes will keep on rising. Based on this, we separate them into different fractions, and then we take those fractions and they all have their different uses. So you guys don't need to know basically what the fractions are. You guys can take a look at the general use. If they do give you use, it will literally be like a 1-mark question. Where do you use this? Like that. But you're not going to see any of this in detail. You just need to know the basic principle that you are separating the crude oil into different alkanes or different hydrocarbons or different fractions based on their boiling point. That's it. That's all you have to know about it. Okay, now go ahead and tell me about cracking. What is cracking?
When you break a long chain molecules and get smaller chain alkanes and alkenes and hydrogens.
Yeah, you get smaller chain alkanes and an alkene. That is basically cracking. There are two types of generally cracking. You have got your thermal cracking and you have catalytic cracking. Okay, catalytic cracking is when you use a catalyst, and thermal cracking is, of course, when you go ahead and you actually use high temperatures to break it down. That's fine.
Miss, do we need to know like what catalysts we need, or like?
Generally, the catalyst that you need is known as zeolite, which is a mixture of aluminium, silicon, and oxygen. If you can remember it, that's very good. But if you can't remember it, that's also fine. But generally, it's a mixture of aluminium, silicon, and oxygen. Okay. Does anybody know what reforming is?
No.
Reforming is when you take a straight chain alkane and you turn it into a branch structure or a cyclic structure. So when you talk about it, your straight chains alkanes don't burn very efficiently. When you take a straight chain alkane, they don't burn very efficiently. So what you can go ahead and do is you can make them undergo a process of reforming, where you can turn them into either a branch structure or a cyclic structure. So because of that, they burn much more efficiently, which is better for your engine, which is better for the environment as well. Okay, then let's go ahead and talk about the different chemical reactions of alkane. First of all, we have our combustion reactions. What do you know about combustion reactions of alkane? And in that, of course, you can, I want you guys to tell me why we do it. I want you guys to tell me what the general reaction is, and also the concept of pollution related to combustion reactions.
You sorry, you will like burn alkanes because they can be used as fuels.
Good job. Correct.
Like
so you can use, yeah.
I think the shorter chains one are like better used as fuels. And
Yeah.
when they undergo combustion, they always produce carbon dioxide and they all produce water and carbon dioxide, sorry.
Yeah,
And
that's
when they
complete
do that,
combustion.
that's complete combustion. And sometimes
Yeah.
they can form only carbon monoxide and water, which is incomplete combustion, which is bad for the environment because CO is
Okay.
like
Yeah.
toxic.
Now, when you talk about pollution, so in pollution, you are getting three major pollutants from your combustion of alkanes. Okay. So one of them you've already mentioned is carbon dioxide, which comes due to incomplete combustion of your alkanes. Now, tell me in detail about carbon monoxide. Why is carbon monoxide actually bad? What does it do?
When you inhale it, it bonds to hemoglobin.
Correct. And then?
And it blocks oxygen.
Yeah, exactly.
Bonding to it.
It doesn't block oxygen. It binds to hemoglobin, making carbomonoxyhemoglobin. And because of that, because it has occupied hemoglobin, oxygen is not able to bind to it. And as a result, oxygen is not transported throughout the body. And what will happen? That causes people or victims or people who are suffering from carbon monoxide toxicity to start losing their consciousness because they're not getting enough oxygen in their brain, and eventually they can end up dying from it. It is odorless, it is colorless, so it cannot even be detected easily. That is one thing. Good job.
But it
Can
has
you
a
tell
smell,
me any
yeah.
other pollutant? Sorry?
But it has a smell, right?
No, it is odorless. Carbon monoxide is odorless, it is colorless, it does not have any smell. So you can't detect it. That is one of the reasons why it is so fatal. If it generally, when you talk about your natural gas, for example, they add odor to it, right? In your natural gas, the gas that you get, they generally add odor to it so that whenever it is escaping, you can smell it and you can detect it and you can, take action for it. The problem with carbon monoxide is that it is odorless. So you can't even smell it, you can't see it. That is why it is so dangerous, because people can't even tell what's happening. They just lose consciousness, and as a result, they keep on inhaling it, and they end up dying. That is one of the reasons why carbon monoxide poisoning is very dangerous. That is the problem. It cannot even be detected.
What about carbon dioxide?
Carbon dioxide also generally does not have a smell. Carbon dioxide is present in your normal air, right? Like around 0.4% of normal air is carbon dioxide. So, I mean, carbon dioxide does not carry any smell either, but carbon dioxide is not fatal for us. Carbon dioxide
if there's high levels of carbon dioxide in the atmosphere, it can have an effect on you, right?
If you have high levels of carbon dioxide, so it would have to be extremely high level, right? Generally speaking,
I heard this thing where like some person left their stove open for like a really long time, and then the carbon dioxide levels in their house were really high, and they started like fainting and stuff.
Generally speaking, what will happen when you're going to be in a situation where there's high level of carbon dioxide, initially your body will try to compensate for it by trying to breathe faster. Okay, when you're going to breathe faster, what is going to happen? It's going to try to remove the carbon dioxide accumulating inside the body, and it will try to take in oxygen. But of course, that is body's response to it. That will happen up to a certain limit. If the levels of carbon dioxide will eventually exceed that particular level, the person is going to end up feeling dizzy. They are going to end up feeling sick because they're not getting enough oxygen. But that is not because of anything binding to the hemoglobin. It's not because of that. It is simply because you don't have enough oxygen available in the air, right? And carbon dioxide toxicity generally in those situations, it is reversible. You shift the person onto a high oxygen cylinder in a high oxygen or pure oxygen, generally you can treat it. So carbon dioxide poisoning, that generally happens when you don't have enough oxygen and too much carbon dioxide. So your body can still survive to a certain extent because your body can compensate for it by trying to breathe harder, by trying to, buffer the pH of the blood. There are different mechanisms that the body has to deal with excess amount of carbon dioxide. But just like everything, body can deal with it up to a certain amount. After that, the body is, of course, not going to be able to keep up with the demand Body is not going to be able to keep up with the demand for oxygen and the person can faint. But carbon dioxide is not that, carbon dioxide poisoning is not that serious. Carbon monoxide poisoning is much more serious, because in carbon monoxide poisoning, first of all, body has no compensatory mechanism. So in carbon dioxide, a person can still survive up to a certain limit, up to a certain time, because the body can compensate for it by making you breathe harder and doing other mechanism. In carbon monoxide, the body does not have any compensatory mechanism. So that is generally much more dangerous. And when you talk about levels, so even low levels of carbon monoxide is very dangerous. Talking about carbon dioxide, generally, you need to have really high levels of carbon dioxide, and it has to be in a really close space for carbon dioxide to end up having any kind of harmful effect. And generally, you can reverse the effect of carbon dioxide easily simply by giving the patient pure oxygen. So the carbon dioxide poisoning can happen, but it's not very common. It is not very common. Carbon monoxide is more common and it's more dangerous compared to carbon dioxide. Okay.
Okay.
All right. Can you tell me any other pollutant that is produced by the combustion reaction?
If there is sulfur dioxide.
Sorry, can you say it again?
Sulfur dioxide or nitrogen?
Sulfur dioxide. Good job. What's the problem with sulfur dioxide?
Is it toxic? Oh yeah, it messes with the pH levels of soil, etc. And it's acidic.
Yeah, so it can react sulfur dioxide. You get two of them. Okay, sulfur dioxide and sulfur trioxide both can end up forming. Sulfur dioxide can end up reacting with the water vapors in the air to give you sulfurous acid. Just want to clear that up, that your sulfur dioxide reacts with water to give you sulfurous acid. H2SO3 is sulfurous acid, right? Sulfur dioxide can also give you sulfur trioxide, and sulfur trioxide can also react with the water vapors to give you sulfuric acid. So both sulfur dioxide and sulfur trioxide contribute.
Where does sulfur come from?
Sulfur is present in your crude oil. So your crude oil generally has, yeah, it has along with carbon and hydrogen, it also has minute quantities of other inorganic compounds. One of them is sulfur. So we can't really remove the sulfur from the crude oil, even though we process the crude oil. And when you go to your petrol station, for example, you'll see so many different types of it depending upon the degree of processing. But despite all that processing, you still have a small amount of sulfur that remains behind. So it comes from there. So generally in car engines, due to high temperature inside the car engine, the sulfur inside the fuel reacts with the oxygen to make sulfur dioxide. That sulfur dioxide can then undergo further reaction to turn into sulfur trioxide. And then when they escape the fumes, when they escape into the air, the same sulfur dioxide can react with water vapors to make sulfurous acid. And the same sulfur trioxide can react with water to give you sulfuric acid. Both sulfurous acid and sulfuric acid contribute to acid rain, in which that acid rain is then responsible for changing the pH of the soil, damaging your plants, changing the pH of your aquatic areas, your rivers, your ponds, your lakes. So they end up damaging your aquatic life as well. And on top of that, they are also bad for your buildings, primarily buildings made up of marble or limestone. They get damaged because of acid rain. So good sulfur dioxide and sulfur trioxide are another pollutants that are produced by combustion reaction. Can you tell me any more?
Miss nitrogen.
Nitrogen dioxide. Nitrogen dioxide. So nitrogen dioxide, once again, nitrogen is generally a non-reactive gas, right? We know that the nitrogen we have in the air is generally non-reactive, but due to the high temperature inside engines, it tends to react with oxygen to give you nitrogen dioxide and to give you nitrogen trioxide. Now, in those situations, what actually ends up happening is that once again, this nitrogen nitrogen monoxide, nitrogen dioxide, they can dissolve in water to give you nitrous acid and nitric acid. This is nitrous acid. HNO2 is known as nitrous acid, and HNO3 is known as nitric acid. So your nitrogen oxide can give you nitrous acid and nitric acid, and again they can end up damaging, causing acid rain, and you can talk about the same effect of acid rain. Nitrogen
You know how
oxide,
in IG we had to learn these reactions? Do we need to learn them over here as well?
they are all mentioned in your book. In your book, they have mentioned all of them, and they're mentioned in your syllabus as well. So if you have the time, they don't ask them quite a lot. You don't see quite a lot of questions related to it, but you are going to get questions related to pollution, related to global warming, related to climate change. You are getting a lot of questions like that these days. So if you can, then it would definitely be a good idea to learn them. Generally, though, this is not very hard. You can make these equations by yourself as well, as long as you remember what the reaction was. Okay. Generally speaking, okay, when we are generally talking about it, your nitrogen oxide, by the way, is also known to cause respiratory disease, right? That is another problem. So nitrogen oxide can cause acid rain, and on top of that, it is also known to cause respiratory disease. So when we talk about removal of all of these, we can remove them by using our catalytic converter. So what happens inside a catalytic converter? Go ahead, and what do you guys remember? What happens inside a catalytic converter? So inside a catalytic converter, what you basically do is you use your catalyst. So you've got multiple catalysts. One of them is platinum. And what you do is that you react your carbon monoxide with presence of oxygen to give you carbon dioxide. There are two reactions that take place. First is oxidation of carbon monoxide. So carbon monoxide is oxidized to carbon dioxide. The second is that you react carbon monoxide with nitrogen oxide. So the nitrogen oxide gets reduced into nitrogen gas, and the carbon monoxide gets oxidized into carbon dioxide. These are the two possible reactions. So directly turn carbon monoxide into carbon dioxide, or allow nitrogen oxide and carbon monoxide to react with each other. They give you nitrogen and carbon dioxide. So nitrogen and carbon dioxide are the products. Generally speaking, this carbon dioxide is also not good for our environment, but it is less dangerous compared to carbon monoxide and nitrogen oxide. So carbon dioxide in it of itself is bad for our environment, but it is better compared to carbon monoxide and nitrogen oxide. Nitrogen oxide causes respiratory problems, and on top of that causes acid rain. Carbon monoxide causes severe health problem. It can be extremely fatal. So that is what the catalytic converter actually does. That is how we remove the pollutants from the exhaust fumes of our cars. But carbon dioxide comes with its own drawback that is known as global warming. Does anybody know how carbon dioxide is causing global warming?
It traps heat and it.
Yeah, good. So it is acting as a greenhouse gas, right? That is what it is doing. There are two greenhouse gases. Do you guys remember the names?
Methane.
Yeah, methane and carbon dioxide. So you have here, it makes a layer around the Earth's atmosphere, which is why we consider them to be greenhouse gases. So generally what happens is that the radiation you get from the sun is ultraviolet radiation. Ultraviolet radiation has a different wavelength, a different frequency. We know that. We've done electromagnetic spectrum. We know that every different spectrum has got a different wavelength. So you have your ultraviolet radiation coming up from the sun. As a result, what happens? The planet heats up. When the planet heats up, it emits infrared radiation. So when the planet heats up, it emits infrared radiation. Infrared radiation has a different wavelength. Because it has a different wavelength, it is not able to pass through the greenhouse gases and go back into the space. So this infrared radiation gets trapped inside and it gets reflected back to the Earth's surface, and it's causing the Earth's surface to heat up. So this is why global warming is happening. The radiation coming from the sun is ultraviolet. It is able to pass through the through your greenhouse gases. The Earth's surfaces heats up. So whenever any substance heats up, it starts emitting infrared radiation. The infrared radiation is not able to cross the greenhouse layer gases, so it stays within
Do
the.
we emit? I mean, sorry, do we emit infrared like when we get hot?
Yeah,
Like if we sweat
exactly.
or something?
Yeah, we also emit infrared.
Really?
Why? Yeah. So haven't you seen those night goggles that in movies and stuff where they have those night goggles that they're using to, do their spy work and stuff? That is all infrared. They're detecting infrared radiation. Your heat strike missiles, you must have seen that, oh, it's a heat strike missile in movies. They all work on the principle of infrared radiation. So they detect infrared radiation, and based on that, they are able to see stuff in the night. So night vision or night vision goggles, they show you humans or objects or whatever based on infrared radiation. So living organisms will be producing infrared radiation compared to non-living organisms. So based on that, they're able to see in the night as well. So we all produce infrared radiation. Any object that is heating up, it is going to produce infrared radiation. Okay, so that is what we have to talk about in terms of catalytic converters. Now, one of the major things we have to talk about is, of course, our substitution reactions of alkanes, right? So we know the substitution of reaction of alkanes is that, for example, we take methane and we make it undergo a reaction with chlorine in the presence of sunlight. So we end up getting chloromethane and hydrogen chloride. Now, there are steps for it, okay? Does anybody remember the steps? What are the steps for it? Does anybody remember? Yeah.
The chlorine, it breaks homolytically.
Yeah, homolytic fission takes place, correct. So what is going to happen? What is homolytic fission?
It happens under UV light, and
it happens. Yeah.
It's breaking of the covalent bond.
Yeah, it is breaking of a covalent bond such that both the atoms get one of the shared pair of electrons. So this is what it is. Okay, you have Cl2, two atoms of chlorine. So when the bond is going to break, they share a pair of electron. So both of them is going to take one electron with them. That is homolytic fission. In heterolytic fission, what will happen? That one atom will take both the pair of electrons. So one atom will take both the pair of electrons. So this is going to end up, for example, getting a negative charge, right? So that is heterolytic fission, when you end up with one object having a negative charge, other one is having a positive charge. That is heterolytic fission. In heterolytic fission, one atom is going to take both the shared pair of electrons. In homolytic fission, the shared pair of electrons are equally divided. So both of them are going to end up getting one electron over there. So what do we call these? What do we call these products that have one unpaired electron?
Free radical.
Free radicals. So free radicals are those species that have a unpaired electron present. So when we talk about these are your free radicals, then what happens next? After the formation of the free radicals, what happens?
A free radical attacks, for example, methane, and it will cause the CH bond to break.
Correct. Good job.
And it will form a carbocation.
Carbocation are generally more commonly seen when we talk about halogen or alkane. It will not form a carbocation.
Oh yeah, sorry.
It will form. It will form another free radical, right?
Yeah.
So this is what's going to happen, that you have your CH4 like this, carbon, which is bonded to 4 hydrogen. This, when it is going to end up reacting with a chlorine free radical, by the way, the direction of the arrows is important, right? For example, when you talk about over here, so the direction of arrows is generally important. So 1 minute. Okay, so generally speaking, your chlorine is going to come and it is going to break the hydrogen carbon bond and it's going to make hydrogen chloride and it will be stable. Then this CH3 is going to turn into a methyl free radical, right? Then this methyl free radical that has been produced, it can go and it can react with another Cl2 molecule. So this CH3 can react with another Cl2 molecule to give you chloromethane and another free radical. Then this free radical then go and attack another possible methane. So the second step is known as propagation. The first step is initiation, which involves homolytic fission. The second step is known as propagation, where the free radicals keep on reacting with other compounds to keep on propagating or keep on continuing the step. Right? So this is what happens, that chlorine can react with methane to give you a methyl free radical. That methyl free radical can then react with a chlorine molecule to give you another chlorine free radical, and the free radicals can sort of keep reacting with other molecules to give you to keep on propagating, to keep on happening. So the chain reaction keeps on happening. So that is propagation. Then after that, what happens?
Termination.
Termination. What happens in termination?
Two radicals will react together.
Yes. Two free radicals can react together to give you a final compound, a single compound with no more free radicals. So termination can be when two chlorine free radicals join with each other to give you Cl2. Termination can be when chlorine reacts with CH3 free radical to give you CH3Cl. Termination can be when two methyl free radical can react with each other to give you ethane, right? So this is basically your three major steps that you're going to end up getting. You have got initiation, you have got a propagation, and you have got your termination step. So, and this entire process is known as free radical substitution reaction. So that is generally that is what you guys need to know about your alkanes. So in your topic of alkanes, you guys need to know about your substitution reactions. You need to know about your crude oil, and you need to talk about your entire topic of pollution. Now, after this, what we have to go ahead and discuss is we have to discuss our alkene. In alkenes, you guys, of course, need to know your addition reactions. And in your addition reactions, especially, you guys have to know about your electrophilic addition reactions, what the mechanism is. So let's start with alkenes. Let's cover it. Okay, so what do we know about alkenes?
They undergo electrophilic addition.
Yeah, they do undergo electrophilic addition. What are the general properties that we know about alkenes?
They're unsaturated. They have a double bond.
They have a double bond. They're unsaturated hydrocarbons. What is their general formula?
CnH2n.
How exactly? How do we get alkenes? Where are alkenes sourced from?
Cracking.
Cracking, exactly. Alkenes are not found naturally in the environment, so they're all synthetic. So we get them from cracking, right? And
they're polar, and they have a pi bond.
Exactly, they have a pi bond present, and there are also they can be polar in nature. Okay. So generally when we're talking about it, so we have to talk about addition reaction of our alkenes. Okay, so we know that the bonding inside our carbon is going to be a double bond, and this is how you're going to draw the double bonding. Pi orbitals are drawn like this, and between the two pi orbitals you have your sigma bond. Then let's talk about our addition reactions, right? So we know that alkenes undergo addition reactions because they have a pi bond. The pi bond is bigger than a sigma bond, so we can break it and we can add our products to it. So when we talk about our addition reactions, we have to know certain addition reactions. One of them is hydrogenation, right? What do we know about hydrogenation?
Alkene to alkane.
Yeah, alkene to alkane, where you're simply directly taking your hydrogen, you take your hydrogen gas, you react it with alkene in the presence of a catalyst. What is the catalyst in the reaction?
Phosphoric acid.
No, not phosphoric acid, nickel. In hydrogenation, in addition of hydrogen, it is nickel catalyst. Phosphorus is for another reaction.
Yes.
Over here, it is nickel. Yeah.
Is this a reduction reaction?
You can call it a reduction reaction if you want, because it is increase in hydrogen. So you can go ahead and if you want to, you can call it a reduction reaction. So this is hydrogenation, right? And hydrogenation is the reaction that we use when we are manufacturing margarine. Okay, so we don't have margarine as much anymore. We all like to eat butter now, but there was a trend a few years
This
back.
margarine has no taste. It's so bad.
Yeah, margarine tastes bad, but you know how you have like your fat diets and you have like new research that comes out. So a few years back, I don't mean a few years, like around good 10, 20 years back,
Yeah.
this research came out. Yeah, this research came out that margarine is healthier than butter. And at that time, that was the research, right? So margarine was, when you are going to talk about it, right? So margarine would be more saturated because they would end up adding more hydrogen into it. So they would end up adding more hydrogen into it. They would end up make it undergo a hydrogenation reaction. And because of that, what would happen that it would be less saturated. So they would go ahead and they would say, oh, that this is better for the diet and this is better now. But nowadays we have again received evidence that saturated fats are actually not that good for health. So we don't eat margarine anymore. But that was the reaction that they were using. They were using hydrogenation to basically make your, they were using hydrogenation to basically make margarine. Then we have another reaction that is halogenation, right? Actually, before we do that, let's do addition of steam. What do we know about the reaction of addition of steam? That we can react our alkenes with steam to give us an alcohol. And in this situation, when you guys were saying phosphoric acid is for this. When you are doing an addition reaction with water, that is what you need phosphorus for. So addition reaction with hydrogen is nickel. Addition reaction with steam is going to be your phosphoric acid. Okay. So when you're going to talk about it, we use concentrated phosphoric acid as a catalyst. The temperature that we generally do this at is 330 degrees centigrade. And generally the pressure is 6 megapascals. So 6 megapascal is your pressure. The temperature is 330 degrees centigrade. And basically what you're going to go ahead and do over here is that you are going to do an addition reaction with water that will give you an ethanol or an alcohol, whatever the number of carbons are. Then we have our halogenation, right? Halogenation is basically when you are undergoing your addition reaction with your halogens. So, and we have seen it in different situations, right? We have seen it in situations where, for example, if I am bubbling any alkene through a solution of chlorine or bromine, what will happen? The color of the halogen is going to change. For example, if I have a chlorine solution and I pass my alkene through it, what will happen? My alkene will react with chlorine to make chloroethane, dichloroethane, not monochloro, dichloroethane. And my chlorine initially will have a pale green color, but as the reaction will proceed, it will turn to colorless. And if I'm doing a reaction, for example, with bromine, so bromine generally has an orange brown color. Initially, as I'm going to start to bubble my alkene through it, the bromine will undergo addition reaction and it will turn into a bromoalkane. And because of that, it is going to, the color is going to turn from your orange yellow to a colorless reaction. So bromine generally is what we use to test for double bonds. So if they ask you, how can you test for double bond, or how can you test for the presence of a double bond, or how can you distinguish between an alkane or an alkene, you react it with bromine water. So if you react it with bromine water, if the color changes from brown to colorless, that means that is a double bond is present. If the color does not change, that means that a single bond is present and it's an alkane you're dealing with, right? So this is your halogenation. And the final thing we have to go over is our, in the addition reaction, is addition of hydrogen halides. And along with that, we also have to talk about our oxidation reaction and of course our mechanism of electrophilic substitution. So we're going to stop it over here for today. In the next class, we'll just go over quickly the rest of the topic of alkenes and start with halogenoalkanes. So then we can finish it up and we can start looking at our past paper questions on the topic. Okay.